Good afternoon. Is the slide visible?
Yes, sir.
Okay, so what we were discussing about in the last class, that is the, just a second. That was the name-based classifier. Okay, that we have discussed. We were discussing, and the main thing in the name-based classifier is that this assumption that instances or data instances what is given to us is conditionally independent given this classification. So that is important. Okay, so that we have discussed in the last class, and we see that the corresponding the maximum a priori probability, that V of map, that we are going to try to find out in this way. Just as a recap of the last class, that V of J, Pj is the classes, this is V of the set of classes, then P given Vj, so this is the class, so what is the probability of basically A1, A2, An. So that is actually we try to find out. Okay, and then we put our Bayes theorem, and ultimately what we boil up, that our naive Bayes is basically standard argmax, the same thing we have discussed it. Vj belongs to V, and P of Vj to I, P of Ai Bj. So this is our ideally the name Bayes. Okay, this is our kind of classification. Okay, so and what if we do, if you formalize this thing, so we find this kind of thing. Ultimately, when we do a classification that X new is a novel or new instance of this dimension, what we said, that our data instance or our data is a kind of vector, and this vector is maybe in this dimension, n-dimensional feature. So the data is an n-dimensional feature space. So we can get the y new in this format, that y new that we are going to classify in this. What is the y new mean, that what is the class of this? That is the argmax. হ্যাঁ শ্যামা, আমি একটু ক্লাসে আছি, আমি হ্যাঁ ক্লাসে আছি, ক্লাসে। So it is argmax, and yk, and probability of y is equal to yk. So what is y is equal to yk? That y is equal to, maybe if it is a binary classification by myself, so y is equal to plus, since y is equal to yk, and then we put this our conventional, what is this thing, and this is probability that x new, xi new, actually this is the new thing of this particular instance is given y is equal to yk. So that is our naive Bayes class. That was what we have seen in the last class. That why this y new is being classified in this way. Okay. Now today we start with an example that how actually this thing we are going to produce with a simple example. So here, what is y? So y is basically 2. This is plus and minus. So there's a 2 class binary class problem. So it's a binary class problem. Binary class classification. Fine. So now this is, we need to know for all such class or such cases what y is equal to plus. So what are the cases? P probability of xi, okay, that what y is equal to plus, and what is the probability of xi? Y is equal to minus. That we have to try to find out. So these things we have to find out. Now, if x is three-dimensional, now let this x, this particular xi means a one instance. Please don't misunderstood that xi is an instant. Every instance is something like that. xi1, xi2, xi3, because it's a three-dimensional. So don't, this I and this 1, 2, 3, please don't confuse. So this xi is basically three-dimensional data. So, and this I is number of instances. I is 1, 2, let's say m. So there's m number of examples. Got it? So this is the I. So x at the three-dimensional, then we have to calculate xi is equal to x1 and y is equal to, what is the probability of this? X is equal to x2, what is the probability given? Y is equal to plus, xi is equal to x3, what is the probability of plus? Similarly, we have to find out what is the a of xi, then in x, y, y is equal to minus, p of x is equal to x2, what is the probability of this? X3 probability of this. Okay. This is a three-dimensional. And if we find this, we can get our values. Okay. Now we give this particular in a more formal algorithmic form. So this is a naive-Bayes algorithm, and one is, this is the x is discrete value. Next we see that if x is a continuous value, then how to do that? But for time's sake, x is discrete values. So xi is a discrete. So this is a training that basically that how to train your naive-Bayes classifier using the labeled sample or the examples, you can say. So okay, so for each value yk, each value of yk, okay, so estimate, we have to, what we have to estimate, that the what is the prior probability. Just for example, if we say that let there is a 3 probability, y is equal to y1, y is equal to y2, y is equal to y3, y is equal to y3. Now the probability of y is equal to y1 is, let's say, 70%. Probability of y is equal to y2 is 20%. And probability of y is equal to, no, so, sorry, I should say indifferently. So if it's a total 100 thing, the total y is equal, when y is equal to 1, it is 70 times it is coming. Is that 20 times? So this is the examples actually. So y3, it is 10 times. So this probability, how are we going to calculate? Then the probability is, it is 70 by 100, sorry, 20 by 100 and 10 by 100. So this is the probability in this way. So this is not the probability. So it is basically that it is three classes, and these are the some sort of you can say frequency kind of thing. So probability is something like this. So this is 7%, 70%, 30%, 20%, and 10%. 10%. Okay. So this is the prior. This is called prior probability. Now for each value of xij. So what is xij? So attribute xi, attribute xi of the jth sample. So this is xij is basically the value of xij is, and if this xij for yk, y is equal to yk, okay, that is estimate theta ijk. Now you see xi is equal to xij and y is equal to yk, and that is for theta. This is kind of a, you can say theta ijk is a kind of parameter. Okay, that's we are basically saying the notation. Okay, so this is theta ijk. Now this is basically the training notations, training, and now it is a testing phase. Now what is a y new? So as we see in the last thing, what is y new? Y new is equal to yk, this capital pi, that means the multiplication of all the i's, p of x new, xi new, or y is equal to yk. So we say the same thing, p is equal to yk, p is equal to y is equal to yk, and this multiplication of pxi new y or yk. So this is because x1 and y I for all i's. Okay, so that particular thing. Okay, so if it is so, then this part p of this, okay, that part is p of x is equal to xi, xij, and y is equal to yk. This part we can write theta ijk. Since it is a, because now xi is new, only thing is now it is new, and this pi k, it is coming from here. That is the prior probability, or you can say the class belongingness actually. So this is pi k. So probability must be 1, so need to estimate n minus 1 parameters. So that is, if we know n minus parameters, last parameter is 1 minus n minus 1 parameters. So it is. Okay. So that is the name base algorithm. So if you have any question, you can ask. Fine. Now, as we know that our y and x both are discrete valued. That was our assumption previously. Now, how actually we use this MLE of this maximum likelihood estimation? Now, how actually, if you given a kind of how you practically apply this thing, given a problem, how are you going to find out some sort of probability or some sort of classification using this? So it is very easy to understand. First, we have to pi k. What is pi k? Is what? Is basically the prior. How we are going to prior means probability of y is equal to yk. And you can say hat for because this is a kind of discrete case, we are basically calculating. So that is equal to number of time d y is equal to y. Exactly what I said. in the last example, and total number of D. So that is, if it is a 70% time, this class belongingness happens. So it is 70 and total D means 100. So it's a 70% of time. Okay. So this is particular. And how are you going to find out theta ijk? This right from here, because it's a big thing. Theta ijk, as we said, that it is the probability of xi is equal to xij. X is equal to xij given y is equal to yk. So it is basically what? X, the ith instance, and ith feature, jth instance. Okay, so this is basically the formula. So that means what? That is how many time this particular thing happened. That means xi, how many times is x? This is capital. Xi is equal to xij, and this is AND function. So and y is equal to y. So this is the thing. So I'll give you example in the next slide, and you can understand very easily that these two probabilities given. These two probabilities given this many times. So we have to calculate how many times this happened. So this and this. So it's AND function. And definitely the total number of time, or the D, y is equal to yk. So if this is y is equal to number of time y is equal to yk, you can get this theta ijk. This is theta ijk. Okay. Number of items is set to D, for which y is equal to yk. So this is the way we try to calculate. You can see next example, you can understand very well. Now, one important thing, it is here, that sometimes here, that a case, let's say there is a 4 class. Sometimes this is y1, y2, y3, and y4. And for a particular case, if in general it is happened when number of samples is very less. In general, I'm saying, in general it is happened this. So it is 70% of time this is y1, 20% of time this is y2, 10%, and this is a 0% time. It is y4. So y4 is a valid class, but it is for a particular case or example, it is, if you are unlucky, it is coming 0. Now, if it is a coming 0, you know, if we say that, we ultimately going to multiply each. And sum of this excise this becomes 0. Got it? What is the problem? Now things will not do work. So in this case, what we will do? We actually use a smoothing. But smoothing is very easy things actually. Smoothing means we initiate, there is some initialization kind of. It's a very low initialization to make any probability is a non-zero probability. So generally we put L for this pi k thing, it is L. And if the number of times, number of R is the number of time that y is equal to, that is basically total number of time, how the y is equal to yk happened. Okay, so this R is that, so L into R. So if we say L is equal to 1, and then we can put this 1 into 100, something like that, because R is 100 times. Okay, so this is just for all relevance, that this imaginary examples we see just due to. Similarly, same thing, it is that here, if theta ijk, if this equal to that this kind of thing, this occasions is never met. Okay, if this is the case, then it give you a problem. It becomes 0. So if I say theta x of I is equal to x ij, when theta jk, if I say that, sorry, this theta jk when is equal to x xij, that this many time is initialized, that L imply by L plus L into m, or sorry, this is capital. So okay, so total number of time, how many time xij occurred, okay, for y is equal to yk, how many time, that is the m, and it is into m. So this is a compensation. So it only if that is a non-zero value. It's a very less value, but a non-zero value. Okay, that is called smoothing. This is just a kind of terminal case handling that terminal cases. Okay, let's say one example of how actually you are going to use this. Now you see this xi is how many dimension? Xi is basically that value of, you can say, outlook, temperature, humidity, and wind. So there's a 4. So x1, x2, x3, x4. 4 dimension. Okay. And the class is play tennis. Is a binary class. It is y1 is equal to no, y2 is equal to yes, something like that. So tennis, play tennis, yes or no. So 2 class. Okay, and this is the different. These are the instances. How many instances? A number of data samples. It is basically number of samples is 14. So it is d1 to 14. So now if d1 is sunny, then this particular a sample, if it is sunny, hot, high, humidity is high, and wind is weak, so it's not suitable for the play tennis. While if it is overcast, outlook is overcast, and temperature is hot, humidity is high, and wind is weak, then it is a yes, and so on. Okay. So these are the different parameters where we can play tennis. Either we play yes, tennis yes, or it's a good for not to play. So these are the training data, actually training data example. That is a training example is given to find out the given a day. Now what we're going to see, that if we say that okay, outlook is, let's say, sunny, but temperature is cool, the humidity is high, and wind is strong, are these particular days good for play tennis? So that is the basic idea. Okay? That we are going to, what is the yes or no? So basically this is the true probability. So that we have to try to find. So how you can do this? Using this naive base, actually. Using your naive base. Okay, so see. Now at the learning, this is the learning phase. What do you mean by learning now at this? Now you see that if the day outlook, if this, you can see here, this is xi and this is x1, x2, x3, x4. That means instance, sorry, So if I means outlook. Okay. And for instance, J, or day G, day something. Now, if we say that, if we calculate this thing, that for outlook, what is the probability that we can play tennis? So the outlook is sunny and play is equal to yes. Okay, so this is the actual your, that is 2 by 9. Now Sam, you can say play outlook is sunny, play no, this is what, 3 by 5. Okay. So that actually this is being given from here. So how many times it is been given, yes or no, that depends on that. Okay. So in this way, we are, for all these uh, feature, that means outlook, temperature, wind, humidity, we basically trying to find what are the different instances, in not instances, this is the position, and what is the probability of what look is overcast. The play is 4 by 9, not play is 0 by 5. So here you can say 0.55. That is the problem. Okay. If this is a, that it requires moving. Otherwise, you need the everything is. This is the theta ijk. So these equations, these things, that means the training has been done for theta ijk. If you know these values, so these values actually theta ijk. And another thing, y is equal to p is equal to y is equal to y yk, that means play. What is the play? Yes. Y is equal to play one play. Yes, it should play. Yes, sorry. So what should we write? Probability play is equal to yes. How many times? Here you see, yes, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5. So total 14. It is 9 by 14. So it's 9 by 14. You get it? And it is 5 by 14. That is no play. So this is the prior. The priors. Okay. Now you see, is a testing. टेस्टिंग में क्या आएगा? So एक x bar आएगा, new point. And what is this thing? What are the its feature? That outlook is sunny, temperature, and so the temp, school, humidity high, wind strong. Okay, so this is, if this is the case, we have to find out that play, probability of play yes is what, and probability of play equal to no is what. That is, we have to find out. Okay, so lookup tables achieved in that learning phase. So this lookup table is this. Is a lookup table. At this we can get this probability out of this. And when what we can say that outlook with sunny, the play is equal to ES is 2.9 and something like that. Okay. Now decision making with map rule, now we have to how to decision. What is the probability that yes? What is the probability the plane is? What is the probability of the play equal to yes given the x bar? What x bar? X bar is this. Okay. That we have to going to find. So the probability is basically that what P sunny, because it's a sunny, what is yes? P cool, it's a cool, what is yes? P high, what is yes? And wind strong, you have strong, what is yes? This probability is required into what is the probability? That is one. That is actually this sigma. This is the capital pi, but I'm writing in this way. And what is the play is equal to yes? Play is equal to yes equal to what? Play is equal to yes. Okay. So these values you can get it from here. And if you put it down and with this play is equal to yes is what? What probability? We know that it is 9 by 49. And we put these values. The sunny, yes. What is the probability? Sunny, yes. You can get it here from here. That sunny, yes. 2 by 9. So you can put 2 by 9 here. Then cool, yes. Cool, yes, 3 by 9. This is 1 by 3. Then high, yes. Yes, 1 by 3. And strong, yes. Again 1 by 3. Into this. So if you all these things you do, you are going to get this value 0.00953. And if it is a no, the same way you can get. Okay. So since play, definitely you can see that play no is greater than play yes, given this x bar, the we label x bar is a no. So x bar, so x bar is basically p of y x bar. This is that. So in this way, we can show that in this using this naive base, we can get it. Okay. Have any question you can ask? It's very much straightforward. Okay. Now, the thing is that this assumption of conditional independence, it bit a strong assumption. That means it is not always the xi are not really conditional independent for most of the practical cases. Okay. So xi not really conditionally independent for most of the practical. Okay, but still you can say we can use naive base in different and it giving a good result. Surprisingly, often the right classification even when not in the right probability. So the thing is that naive base is a very well performing even with this strong assumption. Okay. So naive base, generally naive base is used for the character recognition kind of problem. Still, the people use naive Bayes, and it's surprisingly perform very well. Okay. Now, as of now, we said our x is discrete. Okay. Now, if x is continuous, okay, but still y is discrete because it's a classification problem. We are doing the classification and y is discrete. So this is the algorithm for that the continuous values feature. Now this is it is very easy that we use that what is the x, how this x is being can say represented, that x is Gaussian in nature. That is the in this example Gaussian in nature. So conditional probabilities are often modeled with normal distribution. Okay, so conditional, this is the conditional probability x is basically this continuous valued feature. It is a continuous, but in the cosine, this follow the. This is a very well observed. This is a very well observed most of the time. Lot of time, we should not say most, but it happens. So then, what is the probability of this? What is the probability of this thing? P of xi is equal to x, given y is equal to yk. That time we said that just for basically that was if case of discrete, we can take it as a kind of just frequency kind of thing. This many times it happens by total number of times. But here you have to use your that since it is a Gaussian distribution, pi of ik of 2 pi e to the power minus x minus mu ik whole square by 2 sigma square at ik sigma square. So this is the actual, you can say, the normal distribution function. So sometimes we assume the variance in independent of y, this is sigma I, or independent of x, this okay, or both, it is sigma. Okay. This is something like that. So how we do that? Do this naive Bayes algorithm. We use this continuous for this continuous x, right, and discrete y. The train the naive Bayes example. What do I now? This is the examples given. And what do I mean by training here? So for each value of yk, now what is yk? Yk is, now we know that is basically yk is the for each value of yk we have to try to find out the sigma is pi k. What is this? The probability of y is equal to yk. But this is discrete, that is the same thing. Okay. So how many times it is this? Okay. Now for each attribute, xi, this is the exam estimate class conditional mean. So we have to estimate two things, mu of ik and variance of ik. Okay, so this actually we have to take care of these two things. So that means training means we have to find these two things based on training. Actually this means based on training example. So that easily been can be, we can, this is the way I will show you what is the value of y can. So that thing we have to find out. Okay, what is the this? What is this? If we know these values, mu is equal to ik. So this is called class conditional mean. So it's called class conditional mean and the variance. Okay, so this, if we know this, then we training start. And definitely it will going to understand from the training exam. Okay, now how we're going to train it? Now we use a, this is y discrete and y xy is continuous. We use the maximum likelihood. So what is this? That for 1 by y is equal to j is equal to ik. So this is discrete, so it's not a big issue. So what is sigma? This is the value that sigma is basically a binary uh, valued output, that is this of z and z is true or else. So 1 yj is equal to j, it is 1, and 1 y is equal to not is equal to j is 0. So it just count and it is sum, it's how many times y is equal to y. That means this. So 1 by this. Now this is summation. What is this? Jth training example, you can say. Jth training example. And this is the ith feature. So what is the ith feature? So its ith feature means how many dimensional it is. So if it's a 10 dimensional, its I is one feature. Okay, so mu of ith feature of jth training example. So that is ith feature of jth example. So you can say that for how many number of j is equal to, let's say, 1 to m number of training samples, and I is equal to how many dimension, 1 is to n dimension. Okay, so these two things. And then definitely it is, what is mu ik? It is this equal to when these values xij, so xij, this feature is hold, when yj is equal to, sorry, yj is equal to yk, because it's the jth instance, yk. So this is true. If this is true, then you can. So that many times. So ith feature, jth training example for, if it is for kth class, that will guess the mu ik. It will give you sum it up on this. Similarly, how many variance? Variance is similar thing. That the same thing here, only it is xi minus mu ik. How the different is this? This particular is how the different from the mean for y is equal to. So these two are mean and variance. That is class conditional mean, class conditional variance. And if we know these two, these two we know by these equations. Okay, so we can say that we can put it here, that y is equal to yk, this sigma is equal to x, sigma is equal to. So here, if you know all these two things, we easily find that normal, the xi nu is given to you. These are the values. What is the feature values? And what you calculate is ik and sigma ik, that you have calculated. So you know this, that means you train, and you can put these values and get this and put it in the normal distribution. That means this equation. This equation is put and you get the values. Okay. So this is, and it sum it over a sum it. No? So it is this product of this product of all i's and pi q. No. So probabilities must be summed to 1, so need to estimate only. So you can get what is the probability of x nu, y nu. So probability of x nu is equal to yk. So this probability you can get. Sorry, y is equal to yk given x nu. That probability you can get. So this is where that our variable is continuous. These x values are continuous. This is already done. And here some example also been given. So you can get from this. So you can get u yes, human mu yes, mu no, and sigma yes, sigma no. These values you can get, and you put what is the p of x. You can put in these values here, and we can get these values. Get these values. So this is the value, and so you can put it and you get back these values. Okay, these are the class conditional. This is the class, the prior probability of these values. The temperature is naturally continuous. Fine. So this is, we conclude this naive base. But one thing still, this naive base classification, the major problem is that we, in this case, we can say that this is conditionally independent. Okay, so this thing is a very some problems is that with this naive base. So in the next class, we try to find out that now there is two things. One is if we find out this p of yk, then this is x1, x2, x dot 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 xn. And if you say this not conditionally independent, not conditionally, not conditionally independent, it is mathematically intractable. So there's a lot of computation. But even if you say that, okay, that yk, xy, x2, xn, this thing that is conditionally independent, this to some extent, to somewhat impractical. So this is to extreme cases. Okay. So can we face some sort of intermediate case where sometimes conditional independence and some causal relation or some dependence, that we'll discuss in the next class. It's called Bayesian network, how actually Bayesian network. Okay, with this I conclude this today's class. Thank you very much for attending this class. Please don't go, I just take a your attendance so that we can see. Okay, thank you very much.